It began on the warm, humid night of July 21, 2025, when a camera on the volcanic slope of Haleakala, part of the Asteroid Terrestrial Impact Last Alert System network in Hawaii, spotted what initially looked like another faint spot in the star field. At 8:14 UTC, an algorithm trained to recognize inconsistencies with normal celestial motions raised an alarm. The object was traveling with residual velocity, inconsistent with gravitational capture by the Sun. A few hours later, when independent observations from another telescope in the same network on Mauna Loa confirmed the trajectory, a preliminary announcement appeared on the feed of the International Astronomical Union's Minor Planet Center. For now, it bore a working title with dry indices. But 12 days later, on August 2nd, 2025, after cross-checking the orbital elements, the object was assigned the designation that has caused thousands of people around the world to look at the night sky differently. 3I Atlas, the third visitor from interstellar space, the third and the most difficult to explain. Since the Panoramic Survey Telescope and Rapid Response System detected 1I Oumuamua, a strangely elongated object glowing with a reddish glow, in the fall of 2017, a new era in astronomy has begun. We're used to thinking that visitors come to us only from within the Oort universe, the distant, icy reservoir surrounding the solar system, occasionally hurling long-period comets inward. But 1I Oumuamua came from beyond, with a hyperbolic trajectory and supernaturally smooth light signature. Then, in August 2019, amateur astronomer Gennady Borisov discovered 2I Borisov, a truly interstellar comet, with jets of gas and a dusty coma as we know them. Against this backdrop, 3I Atlas emerged as the third link in the chain, and simultaneously, the first mystery, one that sent chills down the spines of even those who had already been at the forefront of observation, because it combined the features of both its predecessors, and at the same time it defied their logic. The object was extremely dim. At the time of the first Hawaiian images, its brightness indicated an absolute magnitude consistent with a small body, perhaps only a few dozen meters in typical size. But by the evening of July 23, 2025, when the Zwicky Transient Facility on Mount Palomar in California targeted it, it became clear. The light was rotating unevenly, as if the surface of the source of the glare were not a sphere or an elongated cigar-shaped monolith, but something multifaceted, flat, or even composed of several panels. The periodicity of the reflections seemed too precise to be random. An interval of approximately 5 hours and 40 minutes persisted for several consecutive nights. Was this the usual precession of a rotating body elongated along a single axis? Or a reflection from a flat surface slowly turning like a solar sail once set adrift by another civilization? But before we let our imaginations carry us too far, we need to acknowledge the key factor that made 3I Atlas what it is: its orbit. During the first 24 hours, dozens of observatories, from the Panoramic Survey Telescope and Rapid Response System and the European telescopes on La Palma to the South African mirrors in Sutherland, sent their positions against the starry sky to the Minor Planet Center. At the Jet Propulsion Laboratory of the National Aeronautics and Space Administration in Pasadena, a team of speakers, led by celestial mechanics experts whose names don't appear in newspapers but whose precision rivals that of a watchmaker, launched a recalculation. Inclination, eccentricity, longitudinal node, and, most importantly, excess velocity relative to the Sun. The numbers all agreed on one thing. The eccentricity was significantly greater than unity, and the hyperbolic excess velocity was about 37 kilometers per second. For comparison, 1I Oumuamua was traveling at about 26 kilometers per second, 2I Borisov at about 32. 3I Atlas was traveling faster, meaning that the window through which humanity could see it in detail would be as narrow as a crack in a shutter. The exact date of perihelion, the closest approach to the Sun, was estimated at September 17, 2025, at 3:20 UTC, with a minimum distance of about 1 astronomical unit and 5/10. Not too close to expect intense ice evaporation, but not so far away that it would remain completely invisible. However, the moment of closest approach to Earth was expected to occur earlier, on August 29, 2025, at 14:47 UTC. The object passed at a distance of approximately 45 million kilometers. A huge gap in human terms, but a tiny gap in cosmic measurements. It was precisely to these dates that the schedules of observatories and space telescopes began to adjust. The James Webb Space Telescope, with its sensitive infrared instrumentation capable of capturing heat dissipated by dust and volatile matter, added 3I Atlas to its observing schedule for late August, in the narrow gap between distant galaxies and the already scheduled exoplanet transits. The Hubble Space Telescope, despite its age, was called upon to attempt long-exposure visual images. And ground-based giants, from the European Southern Observatory's Very Large Telescope to the telescopes on Mauna Kea, were preparing for a relentless hunt for photons, battling atmospheric vibrations and their own limitations. The significance of such a discovery extends far beyond the latest notable story in the scientific news cycle. Every interstellar object is a message in a bottle, washed up on our shores somewhere off the beaten track. But the difference is that we barely have time to read it. The tide has already carried the bottle back into the turbulent waters. For astronomy, this is a challenge, both technical and intellectual. How can we construct a sufficiently dense observational network in a matter of weeks? How can we coordinate the work of dozens of instruments scattered around the globe and beyond to collect light, heat, and even the possible spectrum of gases if they exist? And finally, how can we avoid being carried away by beautiful hypotheses too early, when oddities in the light curve or minor deviations from a purely gravitational trajectory scream of unusualness, and our hearts cry out, "Tell me, this is it." The discovery of 3I Atlas became a story of collective vision in its first days. While the asteroid terrestrial impact last alert system algorithms were flagging the object in Hawaii on the night of July 21, 12 hours later, amateur astronomers in Europe opened their domes and captured the same spot with knife-edge exposures. Panoramic surveys like the Panoramic Survey Telescope and Rapid Response System leisurely combed swaths of the sky and dredged up archives from recent weeks, searching for so-called pre-discoveries, when an object had already flickered in images but remained unnoticed among thousands of others. On July 28, 2025, a researcher at one of the university centers found a frame from July 9 in which, upon close inspection, a faint trace could be discerned, another pin marking the trajectory. With each such discovery, the orbit was refined, as if the contours of a figure on glass were becoming sharper. Soon, the International Astronomical Union, relying on a report from the Minor Planet Center and independent calculations from the European Space Agency, confirmed its status. The third confirmed interstellar object, named after the system that first identified its non-solar origin. With this name came the burden of comparison. 1I Oumuamua, lacking a visible coma but exhibiting slight non-gravitational acceleration, gave rise to a host of hypotheses, from the release of hydrogen from slowly disintegrating ice to the effects of solar radiation pressure if the object is too thin. Cosmologist and science popularizer Avi Loeb, having allowed himself a bold theory about a technological origin, was criticized, but also became an unwitting symbol of a vague feeling. The boundaries of the explicable lie closer than the boundaries of the conceivable.
2I Borisov, by contrast, turned out to be surprisingly normal. Its rock-ice coma, heated by sunlight, behaved like Oort family comets that have grown in the depths of an alien stellar nest. And here was 3I Atlas, with its shimmering reflections as if its flat surface occasionally assumed a perfect angle to the sun, with a hint of gas emissions, but without a persistent photogenic coma, with a small but statistically stubborn deviation from its pure gravitational trajectory, at a level barely distinguishable from the noise of the measurements. It was exhilarating, it was irritating, and it called for caution. Is there room in this story for bold theories? For example, that this isn't just a boulder from another world, but an artifact deliberately constructed by someone who has long understood the laws of light in the interstellar void? Let's be honest. Yes, there is. Especially when, on the night of August 1, 2025, 2 independent observers reported a brief burst of brightness, synchronous within the statistical error margin. If this had been a single event, it would have been attributed to atmospheric turbulence or a cosmic ray striking the camera sensor. But the repeatability, even if imperfect, raises questions. What if the object's surface truly does have an unusual reflective structure? What if this is an aluminum or composite sheet that yields to the pressure of sunlight? A sail that harnesses the stellar wind as an energetic river? Or, conversely, what if we're dealing with a natural object, albeit an unusually thin and fragile one, such as sheets of fused dust generated by a catastrophic collision in an alien planetary system? This is where the key quality of documentary investigation comes into play: the ability to hold 2 thoughts simultaneously.
The first is factual. The orbit is interstellar, the object is real, its parameters are measurable. The second is philosophical. Any conclusion we reach is a function of what we'll be able to discern in these few weeks. The history of 3I Atlas is the history of time, adjusted to the second hand. Even in the first press releases, University Press Services included dates. August 2nd, 2025, the formal assignment of interstellar object status by the International Astronomical Union. August 12th, target inclusion in the James Webb Space Telescope program. September 17th, perihelion. August 29th, closest approach to Earth. Between these pages are thin lines of schedules, nighttime windows of ground-based telescopes, possible attempts to obtain radar echoes with the largest dishes, such as the Green Bank Radio Telescope and the Interferometer Array, IIA, even if the chance is so small as to border on miracle.
All this synchronicity resembled a film crew filming a rare event.
You only have 2 takes, and both are in the rain. For the average viewer, for you and me, the story of 3I Atlas is also a story of how science exploits chance. The algorithm in a dark room on a Hawaiian night embodies the persistence of thousands of people writing code, honing recognition parameters, and verifying star catalogs down to tenths of a second of arc. The center of minor planets is thousands of emails, where image numbers, coordinates, and errors are combined to form a common pattern. Celestial mechanics isn't abstract integrals. but saved nights and lost weekends, so that by August 2nd, 2025, we can confidently tell the world, yes, it's a visitor. And when the words third interstellar object began to appear in the news feeds, the imagination did what it always does. It substituted vivid images for the lack of data. We love stories. We need heroes and villains. We need messages.
And 3i Atlas, with its uniqueness, seemed to be provoking. Read me, or at least try. But let the excitement subside for a moment, and let's listen to the dry breath of numbers. 3i Atlas came from a direction north of the ecliptic plane, with a slightly positive latitude, which hampered initial observations from the southern hemisphere. Its velocity relative to the Sun indicated not a specific known star stream, but a dispersed background. That is, it didn't necessarily originate from some cluster of ejected debris. Rather, it was a solitary object, with a trajectory born long ago and far away, somewhere on the edges of an unfamiliar system. It didn't make critically close approaches to any of the planets, although Jupiter's influence, as always, will slightly adjust the outgoing hyperbola. And this is also part of the mystery. The fewer gravitational encounters, the purer the imprint of origin. Our task is to capture this imprint before it dissolves.
In this sense, the riddle story isn't a television staple, but a precise definition of the scientific agenda for the coming weeks. What is 3i Atlas by nature? A rocky metallic fragment, charred to a dense crust and polished by millions of years in the interstellar void. A fragile agglomerate of dust and ice, which upon closer approach will produce weak jets, thus explaining the small deviations from the law of gravity. Or, dare we say it without blushing, an engineering construct, extremely thin, light, and reflective, using light pressure as a propulsion mechanism. Light curve data alone aren't enough to reach a verdict, but they are enough to ask the right questions. And the most important of them is, will we make it in time? So, we enter the story of 3i Atlas as attentive witnesses. Cameras tremble in their domes, spectrographs await the clear night, and those who believe in the technological audacity of strangers sit on the edge of their seats, alongside those who trust only the laws of ice. We will analyze everything, from the first frames to archival images and space observations, from orbital dynamics to the philosophy of interpretation. We will move from facts to hypotheses and back again, remembering that names and dates are coastal markers in a sea of mystery, where any reflection of light can be either a mirage or a signal fire, and where the third interstellar name, 3i Atlas, sounds not just like a catalog entry, but like a challenge. You have been given one more try. Are you ready? If the first flash of 3i Atlas's history resembles a brief snapshot in the night, what follows is more reminiscent of a montage of multiple cameras, computer screens, and patient humans who don't trust any individual pixel until they've checked its neighbors.
That night in Hawaii, the Asteroid Terrestrial Impact Last Alert System software worked, as John Tonry and Larry Dino intended. Each fresh exposure was compared to a reference clean image of the sky, compiled from dozens of previous nights. The image difference method subtracts fixed stars, leaving everything that is changed in the field of view. A supernova explosion, a satellite's trail, and sometimes even that pesky electronic noise. But the special glory of the modern sky is its selection algorithms. We've long since moved beyond a simple brightness threshold to behavioral features. Shape, speed, direction,
repeatability in a sequence of frames, and most importantly, conformity with the kinematics of what could be a solar system body. At 8:14 UTC, a set of parameters unexpectedly fell out of the solar matrix. The velocity and angle didn't fit the usual combinations.
The Moving Object Processing System software module generated a so-called tracklet, a chain of measured positions, and assigned high priority to manual verification. Everything then followed a long-established yet always nerve-wracking pattern. A brief email notification, a laconic map of the object in the minor planet center, where each new measurement is like a pencil stroke across a 1.5 million page map of the sky. On the night of July 21st, the Mauna Loa telescope, the second eye of the Asteroid Terrestrial Impact Last Alert System, confirmed the shift. On the morning of July 22nd, the first signals arrived from California. The Zwicky Transient Facility on Mount Palomar, accustomed to hunting transients and supernovae, sent a series of short exposures using a non-stationary, non-sidereal tracking. The telescope moved not as if to follow the stars, but as dictated by the object's estimated velocity.
It's a small, almost romantic battle with the sky. The stars turn into streaks, and the suspicious dot remains a dot. That same day, the Haleakala Panoramic Telescope and Rapid Response System, numerous European medium-sized telescopes, and a pair of South African mirrors were all reporting their sights, adding statistics. The commanding atmosphere was created less by press releases than by silent updates. The Minor Planet Center, headed by Matthew Payne, published batch after batch, measurements, uncertainties, and estimated orbital elements. At the National Aeronautics and Space Administration's Jet Propulsion Laboratory in Pasadena, David Farnokia and Paul Chodas of the Center for Near-Earth Object Studies launched everything they had: the JPL Horizons Ephemera Service, Bayesian re-estimation methods for initial conditions, and a solution robustness check against outliers. The first hyperbola looked like a hyperbola without quotation marks.
The eccentricity could be arbitrarily greater than 1 within the error bars, and the characteristic excess velocity was about 37 kilometers per second. But scientific ethics in such moments is the art of braking. A longer observation arc is needed. Pre-discoveries are needed. And so the hunt began in the archives, that same quiet frontier where tiny confirmations are found in old footage. A search for pre-discoveries always feels a bit like forensics. You know the suspect's approximate path, and you return to the CCTV cameras that were watching the same route yesterday, the day before, and 2 weeks ago. Zwicky Transient Facility staff monitored the July nights and, on July 9th, found a faint but consistent trace where the early orbit had predicted. A panoramic telescope and rapid response system soon confirmed another spot in the July 12th sequence.
The Catalina Asteroid Survey, whose archives stretch back years, returned a negative answer. But this negative answer also became part of the picture. The object was too dim until mid-July, or was outside their field of view. A search of the Dark Energy Survey camera on the Victor Blanco telescope in Chile yielded nothing. But the European Southern Observatory database yielded grayscale long-exposure frames, where 2 points, the expected and the observed, deviated from each other by a value within the error margin. Small building blocks merged into a wall of certainty. On August 2, 2025, the International Astronomical Union adopted the name 3I Atlas. And from that moment on, every measurement became more than just a point. It became history. The key figures in such stories rarely appear on screen, but let's say their names. Karen Meck of the University of Hawaii's Institute for Astronomy, one of those who turned One-Eye Oumuamua into a scientific topic
rather than a newspaper sensation, coordinated the first attempts to obtain a spectrum on the night of July 24, to catch those few photons that could indicate whether it contained volatiles, water, carbon monoxide, or carbon dioxide. In Flagstaff, the Lowell Observatory team tried to activate the high-dispersion spectrograph, coordinating the wiring with calculations from the Center for Near-Earth Object Studies. At the European Southern Observatory at Paranau, astronomers at the Very Large Telescope were preparing a jump mode, a short exposure time where the telescope is moved precisely according to the ephemeris to accumulate light from a moving object. A mailing list was sent to the World Network of Medium-Range Telescopes, where scientific teams around the world are filling gaps, asking for any confirmation, especially from the Southern Hemisphere, where the season and weather are often favorable. Technological and logistics teams worked in parallel. The James Webb Space Telescope's planning department is known for its inflexibility. A huge spacecraft with a huge schedule doesn't like surprises. But on August 12, 2025, the object was added to the Target Observation Program. 3 short windows between exoplanet transits and deep galaxy fields. Engineers discussed not only scientific but also purely mechanical constraints. The tracking speed at which the telescope could track a moving target without blurring. The feasibility of using the near-infrared camera, NIRCam, in fast burst mode to avoid losing the object, and the advisability of attempting to use the mid-infrared instrument, MIRI, if they could secure another slot in the schedule. The Hubble Space Telescope, despite its age and finicky gyroscopes, responded more quickly. At the end of July, the Wide Field Camera 3 team prepared a non-stationary tracking mode and booked several orbits around Earth for the end of August, when the distance to the object would decrease and the chance of seeing even a tiny coma would increase. Meanwhile, ground-based networks were doing what they do best, stitching together a delicate quilt of photometry and astrometry. Photometry is the measurement of brightness. Astrometry is the measurement of position in the sky, accurate to tenths of an arcsecond. They always go hand in hand. Without precise astrometry, you won't be able to catch an object tomorrow. Without reliable photometry, you won't understand its rotation or shape. Over the first 10 days, light curves collected by the Samuel Ocean Space Telescope on Palomar, university observatories, and amateur installations with good optics began to hint at a periodicity of about 5 hours and 40 minutes. It looks like rotation, but it's important not to overstate the familiar imagery of the word rotation. If the body is highly elongated, the signal will be irregular and jagged. If it's flat, it will be sharper at the peaks when the surface faces us directly. And so the first peaks seemed too sharp. Options, from geometry to surface properties, lay on the table like cards. Reflectivity, texture, possible panels. Scientists suppressed smiles. Journalists wrote about the sail, and the wording speculative requires confirmation carefully appeared in reports. The hunt for the spectrum was, as usual, a close call. At the end of July, the European Southern Observatory managed to conduct a series of short exposures using the X-shooter spectrograph, which can cover a wide range of wavelengths in a single set. The signal was borderline. Traces of sodium? A hint of carbon? If we were talking about an ordinary comet, this would be enough for a humorous toast in the Andes. But with 3i Atlas, scientific conscience demanded much more. Then, radio interferometers came into play. The Atacama submillimeter array was reconfigured to detect molecular lines of carbon monoxide and hydrogen cyanide, classic markers of cometary activity. Calculations showed that with the expected low activity, the signal would be weaker than background.
Nevertheless, in the first week of August, a short test observation was attempted. The result was negative, but even negative results are not a waste of time. The boundaries of possibility have narrowed. This means that if there are volatiles there, they are in small quantities. And if they are small, then the non-gravitational effects, those barely noticeable trajectory deviations, must be explained by something else. The radar line naturally found on planetary asteroids closed here almost immediately. The Goldstone Solar Planetary Radar System estimated the power, at distances of tens of millions of kilometers. The desired echo from a volume of tens of meters would be orders of magnitude lower than the noise. The Green Bank Radio Telescope and the Very Long Baseline Radio Interferometry Network were discussed as potential receivers if someone, something, obediently responded to our beam.
But science isn't science fiction, and so these discussions remained behind the scenes. We have eyes. We don't have a voice to be heard. We listen for light and heat, and we must do so quickly. By the end of July, the collaborative architecture resembled a well-coordinated weekly editorial. In the morning, Greenwich Mean Time, the Minor Planet Center published updated ephemerides, calculated using all the measurements received overnight. During the day, the Jet Propulsion Laboratory of the National Aeronautics and Space Administration updated the ephemerides page of the JPL Horizons service, providing everyone, from large telescopes to amateur telescopes, with the same coordinates for the coming nights. By evening, mailings were sent out to Europe and Africa requesting specific windows. Within North and South America, by contrast, reports arrived. What had worked, what hadn't, where the clouds were, where the thin crescent moon was interfering.
This geography of time is always fascinating. When dawn breaks over Paranal, Hawaii is just waking up, and what was captured there during the night could plug a data hole that would otherwise consume thousands of hours of calculations. Thus a trail is built, one dot after another, like glowing manhole covers on a night road. In such stories, technical details are not just tools, but also heroes. Catalogs of stellar positions, particularly those of the European Space Agency's Gaia mission, provided astrometric support down to milliarc seconds of accuracy. This isn't a luxury, but a necessity. When trying to capture trajectory deviations of fractions of an arcsecond per night, any systematic error in the position of the reference stars will turn into phantom accelerations. The models of light reflection from small bodies, for which asteroids in the belt between Mars and Jupiter were observed for decades, turned out to be our psychometry. By comparing light curves at different phase angles, they allowed us to distinguish a sphere from a sheet, a rock from an ice cube, a smooth surface from a rough one. And finally, a worldwide network of software, from image subtraction packages to data sharing services, transformed individual observatories into a single instrument. This work particularly subtly revealed another theme: how cautiously science approaches bold hypotheses. The non-gravitational acceleration, barely visible in the first weeks and unstable, like a vision after a sleepless night, demanded an explanation. The classic scenario is the jet recoil from the evaporation of ice, creating jets.
But if there are few volatiles, as spectra and radio observations indicate, where does the effect come from?
Then, in expert reports, the force of radiation pressure appeared more and more frequently, a subtle push provided by a stream of sunlight. For ordinary stones and lumps, this pressure is negligible,
For very thin ones, with a large specific area per unit mass, it is noticeable. And this means either we are dealing with an unusually porous, low-density material, something like compressed air dust, or, yes, we must admit this word, with a structure, thin, light, one that catches light like the wind. To avoid turning this "or" into a slogan, telescopes extracted everything they could from the sky. By late August, one thing had become intuitively key: small fluctuations in the periodicity of the light curve.
If the body is purely natural and is an elongated monolith or a loose lump, its rotation period changes slowly and predictably under the influence of the Yarkovsky-O'Keefe-Radzebsky-Pajek effect, associated with uneven thermal radiation. If, however, the system is subject to variable radiation pressure on a plane, and the plane can change orientation, then the modulations will be different. At the universities of Iceland, Hawaii, and Canterbury, Michelle Bannister and her colleagues' teams synchronized processing so that on the same day, when the Hubble Space Telescope and the James Webb Space Telescope were looking at the sky, they could blink together. Subtract, add. Run through models and say, "Look, we see." Or, "We don't see." And this "we don't see" is no less valuable.
At the same time, something else important was being done institutionally, preparing data for posterity. Raw images, calibration files, current versions of ephemerides, weather reports, all of this was being stored in open repositories. We already know from the experience of One Eye Oumuamua how much second readings can yield months and years later, when new models, new computing power, and new geometry of questions emerge. In this sense, the history of 3i Atlas is not only a race for the here and now, but also an investment in future reconstruction. Perhaps someone in 2027, rechecking the August images from the James Webb Space Telescope with a different calibration, will notice a thin line in the tail of the spectrum, which we now consider noise. And yet, despite the deliberate resistance to sensationalism, the human element in this story breaks through the details. The night of August 1st, 2025, two independent bursts of brightness, short as a breath yet coordinated. Emails written hastily in dim offices. We see the same thing. Zoom calls between Pasadena, Honolulu, and Paranal. If this isn't an atmospheric effect, if this isn't cosmic rays, then what? And here, the documentary tone inevitably pauses, because sometimes science is that moment when two people look at the same handful of pixels and decide not to rush to conclusions. They'll blow up their clocks, double-check the synchronization, create artificial frames to test the algorithm, run simulations of reflections from flat surfaces, queue up another night at Palomar. And only then will they say, maybe. By mid-August, it was clear. The observing program had been completed. Ground-based optical telescopes were covering a dense grid of photometry and astrometry. Sub-millimeter attempts had delineated the upper limits of the compositions. The Hubble Space Telescope was aiming for visual deep images in long exposures. The James Webb Space Telescope had prepared the near-infrared range, where even faint, invisible dust can reveal itself with a warm whisper. The Vera Rubin Observatory, scheduled for full operation in 2025, was preparing experimental transient wiring for short sessions to test whether its giant camera could see such fast targets during pauses between surveys. Radio equipment listened to the silence. not seriously hoping to hear a voice, but rather to honestly say, "We tried." And in this work, structured like a musical score, something else became clearly evident. How much the very way we see the sky has changed over the past 10 years. Robot observatories have long since ceased to be exotic, but have become the norm. They never tire, never get bored, and never fall asleep. Archives are not a basement full of cardboard boxes, but a living part of the present. Pre-discoveries have ceased to be miracles and have become a craft. Space telescopes aren't mesmerizing monoliths, but rather participants in a shared work shift, from whom you can ask for 20 minutes in between tasks. And yet, strangely enough, it all depends on people, on the experience to know when to stop, and on the courage to make a guess. Atlas became a litmus test of this maturity. We made it. We assembled it. We didn't say too much, but we also didn't dismiss the bold theory. And when the telemeter logs recorded August 12, included in the James Webb Space Telescope program, August 29, window of maximum visibility from Earth, September 17, perihelion, it became clear. The story was just beginning. Because the story of discovery is always the story of what you're willing to do to make the unknown cease to be nameless. And sometimes, all it takes is one night and one algorithm. And sometimes, it takes the entire planet, which decides to look at one point in the sky to hear if a strange message is rustling there. Trajectories are rarely born ready-made. In the first days after discovery, they resemble chalk scribbled unsteadily on a blackboard. In the case of 3I Atlas, this subtle tremor was particularly noticeable. Its high speed, dimness, and short observation windows meant that each new point in the sky could subtly shift the entire hyperbola. And that's why the story of its journey through the solar system is equally a story of refinements. The first solutions, constructed on July 22 through 24, 2025, over a relatively short measurement arc, placed perihelion, the closest point to the Sun, at a distance of approximately 1.5 astronomical units, sometime around mid-September. This seemed like a convenient number for a cautious press release. But by July 28th through 30th, when the pre-discoveries pulled the orbit back on July 9th and 12th, the picture had changed. The perihelion had moved up to unity.
On July 31st, the Center for Near-Earth Object Studies and the Ephemerides Service of the Jet Propulsion Laboratory of the National Aeronautics and Space Administration published an update. The expected minimum heliocentric distance is about 0.98 astronomical units. The perihelion time is September 17, 2025, at 0322 UTC, with an error of a few minutes. This is not cosmetic. This is the geometry of possibilities. If the object comes closer to Earth's orbit, then our chance of observing it will increase. This means we need to monitor more closely and our calculations more accurately. Such refinements aren't an admission of error, but rather a normal evolution of the data. A hyperbolic orbit required that same excess velocity that turns a wanderer into an interstellar object. Calculations converged on a value of approximately 37 kilometers per second relative to the Sun, placing 3I Atlas at the top of the scale among known visitors.
The inclination of its flight plane to the ecliptic turned out to be moderate, around 20-odd degrees, which explained why the object was more accessible to northern hemisphere observatories in the first weeks, and why southern telescopes were late in joining the fray. The longitude of the ascending node and the argument of perihelion, parameters that usually reside in tables and are of little interest to the general public, had a clear meaning here. They determined the angle from which we would see the object as it passed through the plane of Earth's orbit, and therefore the phase angle, which controls how much light would be reflected back to us. For 3I Atlas, this phase scenario posited that it would be closest to Earth on August 29, 2025 at 1447 UTC, passing at a distance of approximately 45 million kilometers.
This figure is dry, but it becomes a rift in schedules. It was precisely to this value that ultra-long exposures and urgent space telescope windows were scheduling, because the minimum distance meant the maximum apparent brightness, all other things being equal. The geometry of planetary encounters is a separate scene in this investigation, where each giant can play the role of an invisible director. For 3I Atlas, the main characters are the Sun and Jupiter. Mars, Earth, and Venus are extras, whose gravitational pull is only noticeable in the most precise calculations and at the level of debates among celestial mechanics. Jupiter, due to its mass, almost always participates in the final farewell handshake with departing hyperbolic guests. It barely adjusts the speed, barely alters the direction of the asymptote, like a conductor who imperceptibly speeds up an orchestra. In the case of 3I Atlas, calculations showed that there will be no direct close encounter with Jupiter. Its distance from the giant's orbit will remain at a few astronomical units. But even at such distances, Jupiter's gravitational tail changes the outgoing speed by fractions of a percent and rotates the orbital plane by fractions of a degree. For most viewers, this is a trifle. For those who, years from now, will be comparing where it came from with where it went, it is a crucial correction. Fortunately, the situation with Earth turned out to be clear. Calculations showed no narrow keyholes, those tiny regions of space through which, after passing, an object returns to a dangerous trajectory years later. Even if 3I Atlas were not interstellar, but a native body, the chance of any significant gravitational nudge would be negligible. But such checks are still being conducted and published, simply so that the community can see the transparent kitchen where there are no hidden knives on the table. Moreover, in this case, keyholes are not so much a danger as an opportunity. Any subtle change in trajectory is a chance for the next generation of telescopes to catch another such visitor arriving along a family path. When people talk about motion analysis, they imagine trajectories on a star map. But for astronomers, a trajectory is also light in time. The light curve of 3I Atlas, coupled with the refined orbital elements, gave us a picture of a rotation oriented in space in a variable manner. Mid-August revealed that the period of approximately 5 hours and 40 minutes was not only stable, but also breathing over a period of several minutes, as if the body were being acted upon by an external force, very weak and constant, but stronger at certain phase angles. The classic explanation, jet activity from evaporating ice, required a noticeable coma, which the Hubble Space Telescope hadn't seen even during long exposures in late August, and thermal radiation, which the James Webb Space Telescope should have detected in the near-infrared given enough dust. Preliminary estimates suggested little of this. Then came the power of sunlight again, pressure, which, as textbooks remind us,
is negligible for rock, but not at all negligible for a thin slab. This idea can be translated into numbers in various ways. Phrases about a non-gravitational component, equivalent to hundredths of a millimeter per second, accumulated over a day, began appearing in observational reports for August 5 through 10th. To the uninitiated, this numerical poetry means nothing. But for a trajectory, it's a chord that makes a melody recognizable. If such pressure is truly at work, then over a long arc, weeks, it can accumulate a shift of fractions of an arcsecond. This is precisely what astrometry, linked to the European Space Agency's Gaia mission, Catalog, captured. And that's precisely why the consistency of ground-based observations made at different latitudes and longitudes was critical. A systematic error from a single observatory could easily mimic luminous intensity. Consistency, on the contrary, made the hypothesis viable. How did mapping the future path help us? In early August, 3i Atlas crossed the northern regions of the sky, across background fields rich in stars near the summer constellations. By August 15th through 20, it entered zones with lower star density, which facilitated subtraction and increased the chances for medium-sized telescopes. Its closest approach to Earth on August 29th occurred at celestial latitudes favorable for observatories, which reached several tens of arcseconds per minute near August 29. To achieve this, many telescopes engaged ephemeris guiding mode, where the system guides not by the stars, but by the predicted target coordinates, transforming the stars into stripes and maintaining the object's point as a circle.
The second objective is to collect as dense a photometry as possible over a single rotation period. If the brightness peaks are truly sharp, their shape may reveal something about the flatness or segmentation of the surface. The third objective is polarimetry, a discipline that rarely makes headlines. If the reflecting layer is smooth and metallic, the polarization vector of the light will differ from that produced by dust and ice. Several university observatories in Europe and South America have specifically allocated polarimeters for late August and early September to give this discipline a chance. A separate line of research concerns attempts to organize stellar occultation observations. When a fast but small body passes in front of a distant star, the star goes dark for a split second. If such a flash of darkness is simultaneously captured by several observers at widely separated points on Earth, it would be possible to reconstruct the object's cross-section, its actual size, and even its silhouette. This would require ephemerides accurate to within tens of kilometers of the plane of the sky, an almost impossible luxury for such a dim and fast visitor. But a group of enthusiasts from the Occultation Observation Network still calculated and sent out estimated bands of probable occultations for early September. The odds were slim, but if it worked, it would be the shot everyone was waiting for. The forecast for the post-perihelion portion of the trajectory is also part of the dossier. On September 17, 2025, passing perihelion at a distance of approximately 0.98 astronomical units, 3i Atlas was already beginning to fade. Its distance from Earth increased, its phase angle decreased, and any signal, thermal or reflected, weakened. However, it is precisely after perihelion, in the third 10-day period of September, that it is theoretically more convenient to capture a stable, non-gravitational component. The gravitational arc is already well defined, and any deviations are more visible against the clean model. Several teams planned to extend astrometry until early October, as far as brightness would allow. Beyond this window,
The object will fade into the clutter of background galaxies and will disappear from most ground-based optics until better times and larger apertures. Where it came from is a question that gradually transformed from a tangle of numbers into a map of the sky. For hyperbolic wanderers, astronomers favor the term arrival radiant, an imaginary point on the celestial sphere from which their trajectories appear to originate.
For 3I Atlas, early solutions placed a radiant in northern latitudes near the constellations Lyra and Cygnus, but without explicitly linking it to known stellar streams or associations. This is a significant no. If the radiant coincided with the motion of some stellar association and the velocity were similar, one could cautiously guess at its region of origin. Here, however, the background of an interstellar street is a wide, unmarked river. It could have been ejected from a distant planetary system millions of years ago. Or it could have traveled for billions, losing its history with each pass near alien suns. Or it could, and this is already a pleasure to say because it excites, be someone's conscious parcel, which has no address on the envelope, because the address is the entire galaxy. And yet, for all the romanticism, such work values modest precision.
That's why the August bulletins from the Minor Planet Center included laconic lines. Non-gravitational parameters remain unstable. Further observations required. Possible influence of radiation pressure under discussion. That's why the Jet Propulsion Laboratory of the National Aeronautics and Space Administration updated its ephemerides every morning, providing them with error estimates for the week ahead. That's why teams working with the James Webb Space Telescope immediately scheduled check frames before and after the main slot, so as not to be left empty-handed if the 10-hour ahead forecast was off by 1/10 of an arc minute. And that's why, by the way, no one promised a portrait, only a light signature, from which it would be possible to deduce features of shape, size, and possibly surface properties. The high-speed drama deserves special mention. 37 kilometers per second isn't just a figure for comparison with predecessors. It's a pace that dictates the rhythm of the entire campaign. At this rate, every week changes the geometry by tens of millions of kilometers. Every day, by millions. And sometimes this pace suddenly makes obvious what's hidden in static problems. For example, a small difference in the estimated rotation period, which seems insignificant on Monday, results in a phase shift of half an hour by Friday, and you miss the key peak of brightness. This is why, in the last week of August, many teams switched to test boosting their models. They spent days synchronizing the actual behavior of the light curve with predicted reflectance curves for various shapes, plates, bars, clods, and scheduling their schedules to this metron. It's like training an athlete for the 100-meter dash. When you know how they start, you catch their expression in their fourth step. And finally, an awkward but honest point. The 3I Atlas orbital analysis remained live, not static, by the end of August. The open data system meant that a new astrometry package from a private observatory in Spain or a university telescope in Arizona could appear online, and it would suddenly, slightly tighten one of the parameters, narrowing the uncertainty cone for tomorrow. This is no cause for antagonism. It is the fabric of modern science. And that is precisely why, even back then, while preparing this story, we left room for clarification. If on August 29, at 1447 UTC, the distance to Earth turns out to be not 45 million kilometers, but 47 million kilometers, the essence of the story will not change. If the perihelion crawls to 324, even less so.
What will change is something else. The strength of our conclusions, because they will rest on a more solid foundation. And yet, despite all the caution, somewhere between the lines of these ephemerides, a question lurked, making the heart beat faster. If the non-gravitational force pushing 3I Atlas is truly more akin to light pressure than jet recoil, if the shape of its light curve is truly closer to the behavior of a flat surface than to the rotation of a rough rock, if the influence of Jupiter and the Sun leaves no other noticeable traces, are we missing a chance to see in its flight geometry not just the path of a rock, but the root of a structure? The answer lies in the orbital elements, but that's precisely why the next section, about nature, will be a field where mechanics meets materials and dynamics meets engineering. For now, here's the date, the number, and the direction. August 29, 2025, 1447 UTC, 45 million kilometers. September 17, 2025, 0322, 0.98 astronomical units.
These benchmarks hold all our hope of understanding not only how it flies, but also what it is. The most difficult question in this story sounds almost childish. What is it? A stone or a letter? A fragment of an alien world, slowly eroded by vacuum and time? Or a delicate object born of thought and hands, not ours? In science, such dilemmas don't follow a black and white line. And so 3I Atlas has forced two traditions into a cautious dialogue. One is geological, a comet-asteroid perspective where the world is explained by rocks, ice, dust, and light. The other is engineering, where the key words are area to mass, radiation pressure, resistance to micrometeors, and attitude control. And if in 2017, One Eye Oumuamua first forced these languages to converse, now in August 2025, 3I Atlas has made this conversation insistent. Let's start with what's easier to accept: a natural object.
The most mundane facts support this theory. Interstellar space isn't empty. Planetary systems have been born, collapsed, and rebuilt over billions of years, ejecting countless fragments. 2I Borisov has become a striking illustration of this cosmic banality. A comet, just like any other, only alien. For 3I Atlas, the first thing that catches the eye is the weak, if not absent, gas activity. At the end of August, the Hubble Space Telescope failed to detect a stable coma that would have graced its images with a soft ball of diffuse light. The James Webb Space Telescope, according to preliminary estimates from the team's working notes, did not detect a distinct thermal excess, which dust produces even with modest evaporation. Radio interferometric attempts at the Atacama Submillimeter Array, ASMA, did not detect lines of carbon monoxide or hydrogen cyanide.
All this adds up to a picture of a quote-unquote dry body, asteroid-like, dense, possibly covered in an annealed crust of carbonaceous compounds capable of reflecting light in a manner similar to that of D and P-type asteroids in the outer regions of our own planetary family. But here's where the first problem arises. If there are few volatiles, where does the non-gravitational addition to the motion come from? That stubborn, albeit tiny, push, detected by astrometry based on the European Space Agency's Gaia mission catalogs. The classic answer, from jets of evaporating ices, requires at least a hint of activity, which we don't see. You might object, the jets are very few, they are symmetrically directed, and therefore don't create a noticeable coma. But they do provide an integral return. This is possible. One can also recall models that attempted to rehabilitate One Eye Oumuamua as a, quote, hydrogen iceberg, or a fragment of nitrogen ice blown off the surface of a Pluto-like planet somewhere in a distant system. Daryl Seligman and Greg Laughlin once discussed such possibilities in detail, while Rafikoff and others criticize them for their thermal unviability. Interstellar radiation and collisions with dust over millions of years should have destroyed such volatile forms. For 3I Atlas, these exotic ices seem even less likely. We see no, quote, hydrogen respiration, no nitrogen signature, no dust. Its velocity is higher, the observation window is narrower, and any activity were it present would likely stand out more sharply. There's another natural scenario, much more subtle and in some ways modern. Imagine a super loose fractal agglomerate of dust, born from the catastrophic disruption of a comet near an alien star.
Such a space aerogel would have a huge specific area with a tiny mass, like a spider web made of glass threads. Radioactive pressure in such a case would be no joke. Weak sunlight could actually push such a lightweight web. This scenario has long been discussed in the context of dust and small body dynamics. It explains the high area-to-mass ratio without artificial materials. The problem is survivability. An interstellar journey of millions of years is an endless hail of micrometeors and ultraviolet corrosion. Will the fractal network remain intact? Will it collapse into a diffuse cloud that we would simply not see? And most importantly, will it produce sharp, mirror-like peaks in the light curve, like those observed by 3I Atlas in late July and early August? Most likely not. Such structures scatter light softly, without glare. A compromise can also be found in geology.
Plate-like fragments are not uncommon in meteorites.
Shock waves and thermal stresses tear rocks into layered flakes. If such a plate, say, tens of meters across and only tens of centimeters thick, emerged from an alien system, could it have survived, polished to a mirror shine by micrometeor bombardment over millions of years? Space weathering experts will say that a vacuum rarely varnishes a surface. It mats it. On the other hand, the melting of microdust during hypervelocity collisions can create glassy crusts, and thermal redistribution can smooth the microrelief. Then, sharp peaks in brightness become at least conceivable if the rotational geometry of a plate-like body occasionally produces an ideal angle to the Sun and Earth. This image appeals to those who want to remain in a world of rocks and ice. But it has an enemy in the form of numbers. For radiation pressure to provide a noticeable trajectory boost, a very high specific area is required.
A centimeter-thick plate of rock is simply too complex a scenario. This is where the engineering hypothesis ceases to be a figment of the imagination and becomes an equal participant in the discussion. If 3I Atlas is a thin, lightweight structure, something like a solar sail or a fragment thereof, many things fit together. Where would the specular spot on the light curve come from? From a mirrored or metallized surface, whose microrelief has been emasculating the vacuum for years. Why is the non-gravitational additive closer to radiation pressure than jet recoil? Because the area per mass is large, and there are no volatiles. Why is there no thermal signal from dust? Because there is no dust, and there shouldn't be. Why does the rotation period breathe over a period of several minutes? Because the thin plane is subject to the torque of light, which varies with phase angle, analogous to the Yorp effect, only for a sheet rather than a rock.
In this design, even the absence of narrowband radio signals in the ranges typically used by the Search for Extraterrestrial Intelligence Institute and the Breakthrough Listen program doesn't ruin the picture. If it's a fragment, it has nothing to transmit. If it's a functioning device, it may be silent or not speaking to us.
Of course, the engineering hypothesis has many faces. It's not necessarily the ship with a sail of science fiction. It could be a piece of multi-layered thermal insulation, once torn from a large spacecraft flying between the stars and released into free flight. It could be a protective tile from an interstellar probe, a radiator coating, a thin sensor panel. It could even be galactic junk that we didn't notice until the era of extensive surveys. The critical question is its origin. From what point in the galaxy? From what civilization? For what purpose? The arrival radiant of 3I Atlas, according to calculations from late August, is not tied to known associations. It doesn't point us to a bright star with a hot catalog of exoplanets. But this isn't a killer argument. If space is populated by rare but multi-millennial trajectories of probes and their fragments, we will see a background, not a caravan. How can this be verified without saying we believe, where we should be saying we see? Several key tests are on the table, and the August nights, including August 29, 2025, the day of closest approach to Earth at 1447 UTC, were tailored for them. The first is polarimetry. Light reflected from a smooth metallic surface is polarized differently than light from dust and ice. The dependence of the degree of polarization on the phase angle is the material's calling card.
Several groups in Europe and South America have recorded these curves. Preliminary working reports indicated polarization at a level of a few percent at an angle close to the maximum without pronounced cometary behavior. Not a death sentence, but a hint. The second is the precise shape of the light curve peaks. Specular reflection from a flat surface produces very sharp peaks, and their width depends on the micro roughness. In late August, the Samuel Ocean Telescope on Palomar and several university instruments recorded a stitched collection of dozens of measurements at intervals of several seconds to capture precisely this sharpness. The third is the dependence of the non-gravitational component on the phase angle after perihelion. If the light kick is real, its projection onto the orbit should change predictably, and astrometry at the end of September should show this. Radio silence hasn't gone unnoticed either.
The Search for Extraterrestrial Intelligence Institute used the Allen Array, and the Breakthrough Listen team used the Green Bank Radio Telescope and the South African Meerkat Radio Telescope during the windows of August 28 through 31 and early September. They listened narrowband on the hydrogen line near the rational frequencies and checked the broadband background on the modulation. So far, there's silence, at least in the preliminary reports. But even here, silence is ambiguous. If it's debris, it's silent. If it's a craft, it might be speaking on frequencies we haven't listened to, or in ways we can't recognize. Or perhaps, and this is important to accept, it's not speaking to anyone at all, because it's not a message for us. Skeptics of the engineering theory are holding firm, and rightly so.
They point out that the mirror peaks could be an artifact of rare imaging conditions, and that the recurrence of the August 1, 2025 bursts must be confirmed by more than 2 independent observers. They point out that the object's color indices, based on available photometry, are not crystal neutral, but slightly reddish, like those of carbonaceous bodies, meaning we do not have a perfect foil. Finally, they urge caution when handling non-gravitational parameters. Tiny systematic errors in astrometry at high speeds could mimic a light push, as discussed in the literature on One-Eye Oumuamua.
And these are all arguments not against, but for precision. Against this backdrop, the details of the engineering hypothesis also mature. It doesn't necessarily have to be a perfect sail. It could be a composite with a multi-layer structure, where reflective and absorbent layers produce colors close to those of carbon, and the surface, after millions of years, has become a matte foil, still capable of producing sharp reflections at rare angles. The philosophy of this fork in the road isn't a weakness, but a strength. It forces us to write questions in the fields of observation. If 3I Atlas is a natural body, why does it have such a high area-to-mass ratio? And where does its geometry come from that can produce glare? The answers here lead to catastrophes in alien systems, to the physics of dust destruction and sintering, to new models of the survivability of fragile structures in the interstellar medium. If 3I Atlas is a structure, who made it and when? By a modern civilization hundreds of light years away, or by an ancient culture whose traces have long since vanished with the breath of the galaxy? Why did we catch a fragment and not a whole object? Perhaps precisely because we cannot see whole objects. They are too dark or too rare, and fragments just happen to fall into our observations. Ask yourself, if you throw a bottle into the ocean, years from now, more pieces of glass will float to shore than a note. And yet, for all the journalistic charm of this metaphor, we remain with light and numbers. As of August 29, 2025, the day of best visibility, nothing in the data warrants the pronouncement, "It's definitely artificial." But nothing allows us to close that door either. Avi Loeb of Harvard University and the Smithsonian Center for Astrophysics, back in the One-Eye Oumuamua story, took on the role of reminder. A bold hypothesis is useful, if it's testable. Now, testability has become the very essence of the 3I Atlas observing campaign. This is the maturation of the topic. At the University of Hawaii, Karen Meck is asking to wait for the full reduction of the Hubble Space Telescope data. At the European Southern Observatory, polarimetry teams are consolidating nights into a single curve. At the Jet Propulsion Laboratory of the National Aeronautics and Space Administration, dynamicists are adding explicit radiation pressure to the models and seeing if the agreement improves after perihelion. In the Breakthrough Listen program, engineers are analyzing petabytes of silence, because silence can also be informative. There's another subtle test, one that straddles the line between observability and interpretation. If 3I Atlas is a plane, even a curved one, then on long timescales its rotation axis should slowly precess under the influence of light. This will generate variability in the phase dependencies of its brightness, which can be observed for weeks. Teams in Canterbury, Reykjavik, and Honolulu were already running models in late August where sheet and beam models produce different precessions. Will they be able to extract this effect before the object fades by October? If so, we'll have another compelling argument to add to our list. If not, then this card too will be on the table of future interstellar visitors. And here, between the fields of registers and the fields of imagination, there's a quiet pause. The kind you'd want to leave in a documentary before a close-up. What's more important? Proving we're alone, or proving we're not alone? The wrong question. The right one is how to ensure that next time we have more than a few weeks, more than tiny glimpses, more than a barely discernible non-gravitational note on an orbital score.
Atlas has given us a reason not only to debate nature, but also to reassemble our instruments for such controversial cases.
And when the diaries read, August 31st, first cycle of polarimetry processing completed. September 5th, preliminary peak sampled light curves published. September 20th, post-perihelion astrometry dataset updated. We might be closer not to an answer to what it is, but to the certainty that next time won't find us half asleep. And today, we're honestly keeping both doors open. And perhaps honesty is the best intelligence detector in this story. The instruments we've thrown toward 3i Atlas are like characters in a movie, each with its own character, its own strengths, and its own weaknesses. Some see heat, others the subtle nuances of reflected light, and still others measure positions in the sky with hair-length precision a continent away. They all agree on one thing: we're running out of time, and only cooperation makes chances real. When an object is traveling at 37 kilometers per second and passes 45 million kilometers from Earth on August 29, 2025, at 14:47 UTC, every window, every rescheduled schedule, every request for an extraordinary observation becomes more than a formality. It's a cultural technology where the world is learning to quickly look where it needs to be without losing precision. On Earth, the core of the campaign was formed by survey and flexible optical telescopes, the very networks that, in essence, brought us into the era of interstellar visitors. The Asteroid Terrestrial Impact Last Alert System in Hawaii was the first thread in the eye of the needle through which the entire story was drawn. The panoramic telescope and rapid response system added width, obscuring swaths of sky and revealing pre-discoveries. The Samuel Ocean Space Telescope on Palomar and the International Las Cumbres Observatory Global Telescope Network stitched together continuous light curves from the nights, allowing peaks of brightness to be captured with sufficient precision to argue not about whether there is rotation or not, but about what the surface geometry is. The Vera Rubin Observatory, which was being commissioned as a new standard for survey astronomy, tried its first non-stationary tracking of a fast object during breaks between survey images. It was a risk. The gigantic camera and data stream don't take kindly to improvisation, but it's precisely these kinds of experiments that transform an instrument into a participant in the action, not just a background machine. Space telescopes have become the eyes that see where air obscures. The Hubble Space Telescope, which has endured dozens of missions at the director's request, set aside several orbits at the end of August and switched its wide-field camera 3 to tracking mode. This involved a carefully calculated tracking. The telescope moved so that 3i Atlas remained stationary in the frame, and the stars were stretched into gentle streaks. The idea was simple and daring. If a soft, diffuse glow from the coma appeared during a long exposure, we would see it. If not, we'll at least set an upper limit on the dust and gas, making the jet recoil hypothesis even more shaky. The James Webb Space Telescope, seemingly an even less flexible giant than Hubble, nevertheless found 3 short windows in mid and late August. The near-infrared camera, NIRCam, and, with luck, the mid-infrared imager, MIRI, should have been able to see where even the tiniest dust emits a thermal whisper. If there was even the slightest warm trace there, we would have captured it.
And this if isn't just a figure of speech. On such objects, even a negative result is important, because it narrows the hypothesis space.
From the world of long waves, radio telescopes and submillimeter arrays join the fray. The Atacama submillimeter array, one of the most sensitive machines
for searching molecular lines, attempted to isolate the signatures of carbon monoxide and hydrogen cyanide, classic markers of cometary activity. The plan was short, pulsed sessions during the first week of August, when the geometry was already clear and the object had not yet gone too far. The result was silence. Not absolute, of course. Silence in radio science always signifies upper limits.
But it was strict enough to send a message across the networks. If there are volatiles, there are very few of them. The Near-Earth Object Wide Field Infrared Survey Explorer, an orbiting infrared telescope extending its lifespan in the Near-Earth Object Monitoring format, added several long-wavelength photometry points from low Earth orbit. These weren't artistic photographs, but they did clarify the energy balance. Nothing resembling a dust plume was visible. The field of heliophysics also had something to offer, albeit with caveats. The Solar and Heliospheric Observatory, with its coronagraphs, has been catching comets that wander too close to the Sun for decades. Hundreds of Kreutz comets perish before its eyes. Had 3I Atlas followed a different scenario and dove toward the Sun, we might have had a chance of seeing it as a dot in the coronagraph. But its perihelion, near 0.98 astronomical units, put it outside the best field of view.
The solar orbiter, flying through the inner solar system at an inclination, and the Eugene Parker Corona Explorer, plunging into the solar wind, could theoretically provide rare perspectives. But here too, limitations reigned. Telemetry, targeted scans, safety. It's not easy to get a spacecraft born for the Sun to look at a dim dot far in the sky. Nevertheless, the teams monitored the schedules and discussed windows, just in case the object showed unexpected activity. The most intriguing link in this chain is a distant scout in the Kuiper Belt. The New Horizons spacecraft, led by Alan Stern of the Southwest Research Institute, has already taught us that the outer reaches of the solar system are not an exile, but a laboratory. Its LORRI camera, capable of ultra-sensitive long exposures, and its Ralph multispectral system can provide unique scattering angles. While Earth sees an object head-on, New Horizons can see it in sidelight, or at large phase angles. This is gold for those studying the microphysics of reflection, how exactly light scatters on a rough or smooth surface, whether there are glossy areas, how quickly the brightness changes with angle. In July and August 2025, the spacecraft team considered a fast target, short bursts with LORRI to catch 3I Atlas against a dense star field. The constraints were severe: limitations on the turnaround speed, communication time, and competing objectives of observing Kuiper Belt objects and the heliosphere. Still, 1 or 2 sessions, on a whim, were possible, even if the brightness was at the threshold of sensitivity, even if the frames required weeks of processing. The geometry itself was priceless. The only spacecraft that could see the interstellar visitor differently than everyone else. This is a perspective impossible to obtain from Earth or from the Sun-Earth Lagrange point L2, where our large telescopes reside.
On the very practical front, work was underway that is essential to any poetry: polarimetry, occultations, and the coordination of citizen observers. Several university observatories in Europe and South America deployed polarimeters and began plotting the degree of polarization of reflected light as a function of phase angle. It's a subtle discipline, but it sometimes reveals the material better than all the color indices combined. The International Association of Occultation Observers mapped out bands of likely stellar occultations for early September and sent out instructions. Anyone with fast cameras and accurate watches should give it a try. The odds were slim, But if an object eclipsed a star for a split second, we would get a knife-edge measurement. A network of citizen telescopes, from unistellar collaborations to distributed tenants at remote observatories, provided the background that made the light curves continuous. Thousands of people around the world synchronized their apertures on the same point. And when these amateur recordings formed a neat peak tens of seconds wide, professional instruments knew exactly where to look. What we couldn't do is also important to highlight. Radar, the pride of planetary defense, is powerless over tens of millions of kilometers for an object probably no larger than 100 meters. Even if we combined the transmitting power of one installation in bistatic mode and received with another, the signal would be drowned out by noise. A rapid interceptor mission, a dream born back in 2017 when Project Lyra, a group of enthusiasts at the British Interplanetary Society, proposed wild trajectories for chasing One-Eye Oumuamua, has once again remained a dream. The time frame is too short. Less than 40 days elapsed between July 21st, 2025, when the asteroid terrestrial impact last alert system's first bell rang, and August 29, when 3i Atlas was closest to Earth. That's nothing for the development, coordination, integration, and launch of any spacecraft. So the only way to have a chance is to keep the, quote, charged spring in place in advance. And here, 3i Atlas becomes not only an observational target, but also an argument in favor of new instruments. The European Space Agency is already following this path with the Comet Interceptor mission. The spacecraft will wait at the Sun-Earth L2 Lagrange point and launch toward a, quote, dynamically new comet or interstellar object when one appears. The mission's launch is planned for the end of the decade, and 3i Atlas only underscores its timeliness. This wait-and-go architecture is precisely suited to the pace of interstellar visitors. The National Aeronautics and Space Administration is discussing a project for an infrared telescope to search for near-Earth objects, the Near-Earth Object Surveyor, which by the end of the decade will scan the sky against the thermal background and detect the warm spots of small bodies. It won't intercept an interstellar wanderer, but it will give us a head start of weeks or even months if the visitor is warmer or larger. Behind the scenes, and in proposals for research on promising, innovative concepts, ideas for a ready-to-use interceptor at the Sun-Earth L1 or L2 Lagrange point are being revived. Compact, fast, with a solar electric propulsion system, a telescope, and a dust collector, which could catch up and fly by within a year or two of the alert. These are still sketches, but 3i Atlas is transforming them from futurology into bureaucracy. Requirements need to be written. Mass calculations need to be made. Launch schedules need to be created. There's also humble engineering, which doesn't involve head-scratching launches, but delivers benefits today. These include software interfaces and coordination protocols. The Minor Planet Center, the Jet Propulsion Laboratory of the National Aeronautics and Space Administration, the European Southern Observatory, and the Space Observatory Scientific Mission Archives. All of these systems have learned to communicate faster. When ephemerides are updated daily and automatically pushed into telescope schedulers, when an on-demand request to the Hubble Space Telescope is accompanied by an attached file with a 6-day forecast and error rates at each point, when the James Webb Space Telescope Archive publishes its raw materials faster than usual, allowing ground teams to stitch together the best of both worlds, that's a tool. Not a lens or a mirror, but the nervous system of modern astronomy, keeping hands and eyes in good shape. A key tie that cemented the entire campaign were the viewpoints dispersed across orbits. From the Sun-Earth Lagrange point L2, the James Webb Space Telescope operates, and Comet Interceptor will be waiting its turn in the future. The Hubble Space Telescope looks out from low Earth orbit. From the Earth's surface, from the Atacama Desert to the lava slopes of Mauna Kea, arrays of mirrors stretch skyward. Somewhere in the cold darkness of the Kuiper Belt, New Horizons captures rare angles, and the Solar Orbiter and the Eugene Parker Corona Explorer orbit the Sun. This geometric chorus scene provides something that a single super window can't. Different phase angles, different background fields, different systematic errors.
When you combine a light curve taken from Earth and a photometric point obtained at a large phase angle by a distant probe, and add to them the absence of dust in the infrared and the absence of molecules in the radio, what emerges is what it all started for: cross-verification. Too often, we argue about the nature of objects based on a single instrument. 3i Atlas forces us to build a three-dimensional image. Of course, even in such a well-constructed symphony, there are still pauses and false notes. Clouds on Paranal on a particular night, an unexpected gyroscope failure on board the Hubble Space Telescope, requiring a restart and postponing observations until a day later. A limitation on the James Webb Space Telescope's transmission speed, which prevents it from tracking a target for more than 10 minutes without a break in the series. Data transfer limitations on New Horizons, where every megabyte is precious. All this is the reality of any campaign.
But that's precisely why two other invisible heroes are so important: patience and the archive. Patience means not drawing more conclusions than the data allows and waiting for the processing to catch up with your emotions. The archive means not losing anything that might be needed tomorrow. Raw footage, calibrations, weather logs, ephemeris versions. Oumuamua taught us that a second attempt to read previously captured data can change history. Atlas establishes this as a rule. And finally, a question that goes beyond this specific pursuit. Why do we need all this if this time we might once again be left without a portrait, without an indisputable signature? Because the instrument is built not for a single frame, but for life. The combination of ground-based networks, space telescopes, distant probes, and standby missions makes us different observers. Today, we catch glare and absences. Tomorrow we cover them, and the day after tomorrow, we launch an interceptor from the Sun-Earth Lagrange point L2. And the day after tomorrow? Who knows? Maybe New Horizons or its successor will be in a position where the interstellar visitor will be illuminated from the side so brightly that its thin edge will stand out without question. Then the question, what instruments, will turn into, what other questions can we ask now? This is precisely the point of the current race. We're not just looking at 3i Atlas. We're building a machine that will look better next time. And if this visitor is a letter sent not to us and not now, then at least we're preparing the table and the light for the moment when the letter lands right in our palm. We stand at the end of a short corridor, looking out an open window. That's how one might describe the moment when 3i Atlas passes perihelion and disappears into nights beyond the reach of the human eye. The window closes, but a draft still plays with the curtain. And this is one of those rare instances where a documentary investigation remains without a final frame. Not because someone hid the film, but because a film, by its very nature, cannot end with a single showing. Atlas leaves us with disjointed scenes, brief bursts of brightness in early August, the gentle,
silence of the infrared spectrum at the end of August, and carefully composed astrometry, where the non-gravitational note sounds sometimes softer, sometimes louder. What follows is the work of the scissors and the editing table. Week by week, month by month, the analyses will mature. The curves will become smoother. The models will become more economical.
But it is precisely here, in the space between shot and understood, that it is appropriate to ask not only what is this, but also what does this mean for us? Because such guests don't simply expand our field of vision, they test who we are when we encounter the alien. How does our understanding of the universe change when interstellar ceases to be an exotic adjective and becomes a regular feature? Just 10 years ago, one-eye Oumuamua seemed like a solitary wonder, whose very presence required a special tone from the reporter. Today, the third visitor, Three-Eye Atlas, prompts a more prosaic thought. Interstellar space is not only populated by dust and gas, but also filled with stray debris, like any ocean, shipwrecks, planks, bottles. This doesn't devalue it, it obliges. The regularity of the encounter turns mysticism into work. And the work here isn't just technology and calculations, but a discipline of thought that tolerates uncertainty as calmly as it tolerates exposure. It's becoming easier to say, we don't know, yet we know exactly what we need to measure next. This maturation of science is rarely visible in headlines, but it's palpable in how quickly archives are retrieved after the Asteroid Terrestrial Impact Last Alert System, ATS alert. How quickly the Jet Propulsion Laboratory, JPL, of the National Aeronautics and Space Administration, NASA, publishes updated ephemerides, and how confidently international groups assign roles and avoid stepping on each other's toes. But there's another line, a subtle, almost intimate one. How a person changes when they admit that before them might be something made by another intelligence. For decades, we've been listening to the radio, analyzing the noise, and remaining silent in response. Because such are the principles of caution developed by the Search for Extraterrestrial Intelligence Institute, the International Academy of Astronautics, and other institutes. Don't respond until international approval. Don't provoke. Don't assert without verification. Three-Eye Atlas is more cunning in this regard. It doesn't speak, it shows. If it is an artifact, it is wordless, like stone, but expressive, like handwriting. And here a strange, almost artistic ethic emerges. We are obligated to read handwriting, but not to create a novel. If glare is simply geometry, then that's what we write. Glare is compatible. If non-gravitational push is described by sunlight, then that's what we write. Pushes light. If nothing adds up to a clear picture, let's leave 2 paragraphs instead of 1. This ethic, in a sense, was taught to us by our predecessors, I. Oumuamua and I. Borisov. One gave us the courage of hypothesis, the other, the peace of the norm. I. Atlas forced both voices to blend, like a good duet where neither one speaks louder. What's next? At the instrumental level, the answer is obvious to the point of banality, but it is precisely this that determines the next step. We need increased readiness. The European Space Agency's Comet Interceptor mission,
a spacecraft that will wait at the Sun-Earth L2 Lagrange point and then launch toward a dynamically new visitor, has transformed from a beautiful concept into a concrete argument. iAtlas has made it more relevant. We won't have the luxury of several years to develop an improvisation. We need on-duty eyes and engines ready to launch into the unknown. The National Aeronautics and Space Administration's Near-Earth Object Surveyor project, an infrared telescope that will be used to search for small, warm bodies, promises to provide a long window of time. Extra weeks, extra months. Sometimes that's the difference between missing the mark and making it. The Vera Rubin Observatory brings not only a gigantic camera, but also a data culture. When processing and sharing become a habit, not a feat, each new alarm goes more smoothly. The network protocols exchanged between the Minor Planet Center, the Jet Propulsion Laboratory of the National Aeronautics and Space Administration, the European Southern Observatory, and the Space Archives aren't just IT. They're the lifeblood of future investigations. And perhaps, somewhere on the drawing boards, they're already redrawing a ready-made interceptor. A compact spacecraft with a solar electric propulsion system, a telescope, and a dust collector, ready to be pulled off the shelf when the next 4i comes into view. At the methodological level, such a guest teaches us another lesson: speaking different languages simultaneously.
In the history of 3i Atlas, we saw how astrometry draws on the European Space Agency's Gaia mission catalog and captures fractions of an arcsecond. How photometry from Earth-based telescopes, from Palomar to amateur networks, stitches together brightness peaks over tens of arcseconds. How polarimetry subtly distinguishes dust from metallic surfaces. How the infrared silence of the James Webb Space Telescope becomes not a void, but a hard boundary for hypotheses. How the radio silence of the Green Bank Radio Telescope and the Allen Radio Telescope Array is not disappointment, but clarity. If a signal is there, it is not here. Not like this, and not now. This polyphony of data is not a luxury or a just in case. It is the only way to keep both doors open, to the natural and the artificial, and not lose face. On a philosophical level, and forgive me, on a universal human level, 3i Atlas reminds us of the long scale of time. If it's a natural fragment, it may have been flying for millions of years, polished and scorched. And we are but a moment in time, during which it shone a little brighter. If it's an artifact, it may be older than our languages, and it came to us as a fragment of some unknown structure. In both cases, we are dealing with a density of meaning distributed across vast distances and time. This is sobering. Any pride in one's instruments becomes humbler when one realizes that in this story, we are spectators at a minute-long screening. But it's also inspiring, because the viewer has a choice. Leave the screening muttering about, "I can't see anything," or stay and help set up the projector for the next showing. At this point, another thread emerges: the ethics of contact and the ethics of discovery. What if we one day see something more obvious? A controlled maneuver, a repeating beam, a clear mechanism. International protocols, from the recommendations of the International Academy of Astronautics to the United Nations Principles on Outer Space, prescribe restraint and coordination,
verification by independent groups, the publication of open data, discussions at international forums, no unsolicited responses. 3i Atlas is a soft mode simulator. Controversial signs, ambiguous interpretations, a status that requires neither answer nor refrain from answering, but a habit of transparency. This habit is part of scientific ethics, but it must become part of public culture. If one day any observatory, school telescope, or private array sees something obvious, it's important for everyone to understand. Not panic, not sensationalism, but calm, rapid, and open verification. That's how we respond to such things. That's what a mature civilization is all about.
There's also practical ethics, almost like police ethics. Is it possible, if we're lucky, to try to pick up interstellar debris? If some visitor one day passes closer, would it be appropriate to talk about a capture mission? What are the rights to such a find under international law? Will this change our planetary protection norms if the artifact contains unknown materials or microenvironments? Today, these questions sound exotic, but they should be discussed before there's reason to make a quick decision. 3i Atlas will likely be gone forever, but it will leave behind reasons to write the first lines of future codes on non-contact exploration, on quarantines for materials, on international distribution of responsibility and access to data, if the lucky one isn't alone. These are unpleasant, sometimes boring conversations. But from such conversations comes the ability to seize opportunities and avoid making mistakes.
If we step a couple of turns into the future, we can see how a new discipline is taking shape: interstellar archaeology. It's not a search for radio signals, not cataloging exoplanets, but the study of floating traces, physical, silent, and sometimes controversial. It's data sparse and rich in interpretations, so it requires robust verification methods. It overlaps with planetology, material science, celestial mechanics, and engineering, so it requires translators between fields. It depends on tools that are not in the moment, but at the ready: backup spacecraft, long-term surveys, cultural protocols. 3i Atlas is the first chapter of such a discipline, written consciously, taking into account the mistakes and lessons of 2017 and 2019. Perhaps this is why, even without a portrait, we sense progress. From a set of tools emerges a system. From a set of observations, a scenario. From a set of hypotheses, a field on which we can play fairly. Here, we need to talk about the cost.
Not just the monetary cost, although telescopes and equipment are expensive. And not just the organizational cost, although coordinating time and resources is the work of invisible conductors. It's about the cost of attention. The world is noisy. We constantly divide our attention between news, crises, and figures. To devote weeks of attentive attention to an interstellar visitor, you have to believe it's important. Why? Because through such windows we see not only the object, we see our ability to gather ourselves and work without guarantees of results. It's a costly luxury to work without the promise of a sensation. But it's precisely this luxury that distinguishes scientific culture from curiosity. And if we had to explain to the future why we turned on the Hubble Space Telescope at the end of August 2025, why the James Webb Space Telescope team scraped together 3 short sessions, why the Vera Rubin Observatory took a risk with a non-permanent cable, why New Horizons spent megabytes on images on the brink, the answer would be simple. Because otherwise, we will remain a society that learns only in hindsight. There will come a time when the reports for August through September 2025 will turn into articles, preprints, and reports. One will say, polarimetry did not confirm metallic luster. Another, the non-gravitational component is consistent with radiation pressure for a specific area above such and such. And a third, the thermal signature of dust is below the limit. Somewhere, a neat phrase will appear. The engineering hypothesis remains consistent with the data, but is not proven. Skeptics will breathe a sigh of relief. No sensation has occurred.
Romantics will say, history continues. We, however, will offer a third perspective. An institutional adjustment has occurred that is rarely noticed. We have learned, in the space of 40 days, to do what recently seemed impossible. Retrieve archives. Adjust orbits to minutes. Synchronize ground-based, space-based, and distant data. Keep data openly accessible. Keep rhetoric within the bounds of the provable. And, at the same time, not stifle imagination. This is progress, just on a different scale. And finally, the very reason why such films and investigations are necessary. When the camera pulls back from the black sky and the narrator's voice falls silent for a second, a silence remains, like that heard through radio telescopes. In this silence, there is room for two feelings: wonder and patience. Wonder, because we have once again seen how a vast and fragile world allows something alien to come to it, and yet does not lose its dignity. Patience, because even if we don't know for sure this time, we've done everything to ensure that next time we'll be ready. Atlas, a name that will remain a line in catalogs and a question in memory. An interstellar visitor? Or an alien message? Perhaps both, to the extent that any letter becomes part of the world it reaches. We received this letter carefully, and honestly. We asked the right questions. We've discussed our don't know. We've built the ladders we'll climb next time. But for now, we'll wait. Heaven is in no hurry, but it very rarely repeats its invitations. When the next alarm sounds, we'll have another chance. Whether we'll seize it depends on what we've done today, 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 today,